We're looking at number systems today, and the first number system we're going to look at is really a review. It's the decimal number system. It uses 10 digits, 0 through 9. Each digit will be put in a specific position, which is a power of 10. We've often called that the ones position, the tens position, the hundreds position, and so on. So let's consider this number 583. The first line here shows that my 583 is equal to a 5 times 100 plus 8 times 10 plus 3 times 1. If we look at that in more scientific notion, that's 5 times 10 to the power of 2 plus 8 times 10 to the power of 1 plus 3 times 10 to the power of 0. Just remember that 10 to the power of 0, any number to the power of 0 is 1. That's why we call it the ones position. So as we count in decimal, we'll look at this first. We're going to use up all of our 10 single digits before we start having 2-digit numbers. And we have we'll start with 0 and go all the way to 9. Now pay attention that when we get to 9, what I want you to notice is that we start over again, and it's like an odometer effect. When we've used all the single digits, then we'll start to roll over, and in that rightmost position, we'll have a 0. On the left-hand position, we'll add 1 to whatever number was there. So that gives us a 1, 0, and then we'll just continue to add where we get 11. So we've got 1, 1, 1, 2, and so on. I've just included this number down here at the bottom to show you that that is actually the base, which is base 10, times itself. And the 10 that we saw here is the actual base itself. So the number system that we're really interested in today is binary, because we do so many things and the computer is working with zeros and ones, whether current is flowing or not, whether connection is made or not. It uses 2 digits, 0 and 1, to represent those on-off conditions. Like decimal, each digit is in a position which is a power of 2. And the powers of 2, just to kind of review, would be 1 and then 2, the number itself, the base itself, and then 2 times 2, then 4 times 2, then 8 times 2, then 16 times 2, and so on. So as we look at our number line, as we did in decimal, we'll see that looking at the positions on the rightmost side, we've got the position that we call the ones position, and then to the left of it, the twos position, fours position, 8 position, and so on. The line below shows that we've got the positions scientifically are named 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and so on. So if I throw a quick number in here, a 1, 0, and a 1 in those positions, what I want you to see is that that is 1 times 2 to the power of 0, which would be 1 times 1, 0 times 2 to the power of 1, 0 times anything is 0, and then 1 times the power of 2, which is 4, so plus 4. And in our decimal equivalent, that is equal to a 5. We'll see that on the next page. So let's look at the base 10 numbers with respect to the base 2 numbers, and we start with them using 0 and 1, and when we get in base 2, we've used up, after we get to the 1, we've used up all the single digits in our number system. So now we'll start to use 2-digit numbers, just like we did in base 10 when we got to the number itself, to the base itself. We rolled that 1 over to a 0 and added 1 to the left column or the left position. So that gives us a 1, 0. We don't call it a 10 anymore. I call it a 1, 0. For the next number, we just add 1 to it and we get 1, 1. It's not an 11 anymore. Next we'll go to we've got two ones. We're going to roll those over like the odometer and add one to the leftmost position. And so in base 2, our equivalent of a base 10 will be 4. The number 5 from the previous page where we had 1, 0, 1 in those last rightmost 3 positions, we've got a 4 plus a 1. And we continue to add, and let's continue until we get down here to this. We've used up 4 digits, and we've used them to the max number that we can have them in our base 2. So we've got 4 binary digits or bits. They're all ones. So the very next number would be, roll them all over, or adding 1 to them causes all of those ones to become a 0, and then a 1 carried into the leftmost position. So you'll see that that 10000 is equivalent to a decimal 16. Hexadecimal is the next number system that we're interested in. Hexa means 6 and decimal means 10. So we're using a base 16. We'll talk about this in class, why we use this. But it uses, and in fact you will recognize it from the ASCII table. We've looked at an ASCII table before. Hexadecimal uses 16 single digits, and it just reuses the ones from decimal, 0 through 9, and then we've had to come up with single digits that go beyond that, so we have used A through F. So now let's look at comparing all of these, the numbers, and seeing how we count in each of these number systems. We start out with a 0 for all of the bases. Next, everybody has a 1 because they all have the 0 and the 1. Now you'll see the next time we know that we've used our maximum number in base 2, so we'll roll that over to a 0 and carry a 1 to the left position. So that looks like a 1, 0. Notice that base 10 and base 16 are the same for a long ways up to a particular position. There's 3, 4, and so on. When we get to 9, we know that in base 10 our next number will be a 1, 0. And in our base 16, we know that we're going to call that number an A. Continuing on down to where we've got 15, we know that the next number in base 10 will be a 1, 6, but in base 16, after we've used up all 16 single digits, now we're starting to use 2-digit numbers, and what we'll have will be 1, 0 in base 16, plain old 16 in base 10, and in base 2, we'll have 1 followed by 4 zeros. This will be important for us to remember these equivalencies. We'll go over some conversions in class. Thank you.